So, in this lecture we will be talking about the Verilog hardware description language. Now, before I go into the syntax and the semantics, because there are some features of the language which require a clear understanding of the semantics, what it really means from the point of view of the hardware design and implementation. So, I would like to mention one thing. Verilog may be used by a designer in two different contexts. Number one, you specify a design in this language, you simulate and see that whether your specification is correct. So, here you are not thinking about synthesis, just you are specifying something in a hardware description language, you are simulating, you are looking at the timing diagram, you are happy that the circuit is working properly. But you will have to understand or remember one thing, that when you are using this language in this particular mode, that your objective is to simulate and verify whether simulation is correct. There you are using some features of the Verilog language which is perhaps not possible to synthesize. So, what I mean to say is that the Verilog language or the instruction set or the features, there are two different parts to it. One portion of it is said to be synthesizable, other portion is said to be non-synthesizable. So, you should clearly know that which are the features which can be synthesized and which are the features which cannot be synthesized. So, if your target is to synthesize a design, then you must restrict yourself to the synthesizable subset. Okay? But otherwise you can use others, other features. Other part existing because in many cases you actually may not want to go down to synthesis. Say actually, for example, in some coursework, you want to just learn the language Verilog. Just you want to write some code in Verilog and simulate and see that if it is correct. See, the CAD tool for synthesis is very expensive, but the CAD tool for simulation is very cheap and available. Even there are a number of versions available on the net for free. So that in many institutions, in order to impart training in Verilog, what people do, they teach the language Verilog and ask the students to simulate and see that whether whatever they have written is correct or not. Just I am giving you some examples.
Portion that cannot be synthesized can be simulated.
The portion that cannot be synthesized can be simulated. Like I am giving some examples. There are some instructions to read some data from a file, to print something, to specify delays, that after this statement give a particular delay, then do this. Something like an infinite loop, something like incomplete if statement. So, there are certain things which in terms of semantics is fine, but when you think of the hardware implementation, it becomes very difficult for the synthesizer. That is why the synthesizer does not consider those features at all. Okay. So, we will see these things later. Fine. So, now would be.
So, given a behavioral description,
yes.
A synthesizer automatically synthesizes hardware level.
Given a behavioral description, a synthesizer will automatically synthesize it down to the gate level netlist. Yes.
So the person concerned does not worry about the synthesis part.
Does not worry about synthesis part. There are a number of you can say flags which the user can specify whether you want to optimize or not. There are a number of features, whether you want to incorporate testability or not. There are certain options the user can specify, but otherwise up to the logic level it is fairly automated now.
So
there is no user intervention.
It is fully optimized.
It is fully optimized, but the problem is that once you look at the optimized layout, you will not understand, or you will not recognize your design. Suppose your design had 4 modules, and after optimizing, all 4 modules are mixed together. So you cannot really identify those 4 modules. So a good practice is to do a partitioning at the high level itself, and to synthesize the 4 modules separately, and on the floor on the silicon you place them manually. That is a good trade-off.
But at least the internal design is optimized.
Internal design is optimized. But even at the level of layout, you would like to see that the basic blocks remain identifiable. This is your CPU, this is your control unit, but if the CPU and control unit are mixed together, you may be a little worried. If there is some bug, what to do? Okay. Fine. So, as I mentioned in the last lecture, there are two popular hardware description languages which people very widely use nowadays. One is of course Verilog, other is vhdl. Well, and we also mentioned that in this course we would be considering mainly Verilog. There are some reasons of course, but first let us try to understand some of the differences between vhdl and Verilog. See, the language vhdl, this evolved initially to support higher level specifications, to support system level design and specifications. It did not support low level design, like for example a gate level netlist. vhdl does not support users to specify a gate level netlist, for example. Here you can support system level design where the blocks are specified, you specify the blocks, their behavior and how they are interconnected. But Verilog was designed from the other way around. This was designed by the designers who were developing FPGAs and ASICs, who are more familiar with the low level description languages like logic equations, like circuit diagrams at the RTA level or gate level. So, they designed Verilog from that point of view. So, you will see that in Verilog it is very easy to specify designs from that level. We have already seen some examples. So, the language features are different, as I mentioned. So, let us try to see some of the differences. vhdl provides some high level constructs, because I had mentioned this was primarily designed for system level designs, and at the high level you can have so many different kinds of requirements to specify. So, there are something called user defined types, user defined configurations that are possible in vhdl, but in Verilog these are not there. vhdl, there are no predefined types, all types have to be defined by the user, like integer, boolean, etc. These types are not there pre-existing. But in Verilog, since the primary emphasis was for low level designs, all the basic data types and constructs and the basic gates, they are available as primitives. So, you can straight away start using Verilog to design your circuits even from a low level. Now, in vhdl, if you want to do this, you cannot do it straight away. You will have to import or include something called packages. Packages are something which someone has already written and designed for you. Packages are basically a set of modules where the behavior of all the low level functionalities have been specified to the threadbare detail. So, unless you do this, you cannot use vhdl. But in Verilog, as I told, these things are available as language primitive, they are part of the language. But in vhdl, the data types, the basic gates, the modules you use, they are not part of the language. They have to be imported or included as packages, right. So, if you have the packages, of course, you can use vhdl then, but without packages, the language vhdl is no good. But if you have packages, you can use, of course. But again I am telling you, Verilog is more natural for persons, for logic designers who are more familiar with specifying in the terms of logic, in terms of interconnection of gates, etc. Verilog is a more natural way of expressing as compared to vhdl. That is why in this course we have chosen to select Verilog. Of course, you can also use vhdl, there is nothing wrong with it. So, now let us try to look at some of the language features of Verilog. Fine. In Verilog, the basic building block using which we design everything is called a module. So, a module is the basic unit of hardware in terms of which we can specify the behavior or the structure, whatever. So, the whatever we specify in Verilog, that is in the form of a module. Now, in a design there can be several modules. There are some restrictions that within a module definition you cannot include another module definition. So, a module definition within another module definition is not allowed, but what is allowed is like the example that we had seen in the last class, we had seen we can instantiate, we can define a module externally, we can include it as part of a higher level module, that is always possible. And since this is possible, we can have a nice hierarchy of designs. We can design it using a bottom up fashion. We define the low level modules, use them to design slightly high level modules, use them to design even high level modules. So, using this we can have a hierarchy of designs. We can either proceed top down or bottom up as we wish. The language Verilog supports this. Okay. Now, you have already seen how a typical module looks like, but in terms of the syntax, the basic constituents of a module are these. So, a module definition will start with the keyword module and end with a keyword end module. This is the module name. You will have to give a name to each module. And here you will have to list all parameters. See, if you treat a module as a black box, there will be some inputs to this module, there will be some outputs from this module. These are sometimes called ports. So, you will have to list all the input and output ports out here. Next, you will have to specify that which of these ports are input, which of these ports are output. Well, you can also specify something called bidirectional in input and output both. So, there are some input output declaration lines out here. So, you will have to specify which of these are input parameters, which of these are output parameters, and what are their data types. They are single bit or vector or what. And as I mentioned also in the last class, there can be some interconnection which is internal. So, inside a module you can have a gate here, you can have a gate here, there can be an interconnecting line in between. But this line is neither present in the input port list or the output port list. But when you specify this circuit in a structural form, you will have to give some name here. That will come here, local net declarations. Nets means interconnecting wires. So, this interconnecting wires which are internal to this module, this will come after this. Then the actual specification of your block. Well, here I say that these are parallel statement because here you can specify a number of statements, and you understand in Verilog we are trying to specify hardware. Now, each of these statements will be getting mapped into some hardware blocks. Now if you have several hardware blocks, computation will obviously go on in parallel. Well, unless they are interconnected in cascade or there is some clock or something which is driving them. So, if there is no such thing, all this computation will go on in parallel. If there is an AND gate, if there is an OR gate, they will evaluate together. Right?
If they're in cascade, like
if they are in cascade, for example, if there is an AND gate, if there is an OR gate, they will evaluate in parallel, but the output of the OR gate will get the valid value after 1 unit of time. Suppose these inputs change state, these are the inputs A, B and C, these inputs are changing. So, the output of the AND gate will change first, and after a delay the output of the OR gate will change. So, the gate delays will take care of that.
So does Verilog take care of the gate delays?
Verilog take care of the gate delays. You can explicitly specify delays, or when you are picking up some modules from the library either predefined or otherwise, there are some pre-assigned delays to the gates.
so if we are having a behavioral description of the gate, we are writing it itself.
Well, if you are having a behavioral description of the gate, you can explicitly specify the delay in terms of a number. you can specify this block has a delay of 10, this block has a delay of 5. There are ways of doing that. We will see it later.
Sir, here I did not understand what do you do with this ABC? They are running in parallel, no?
ABC, here I am saying, suppose ABC the values were say 0, 1 and 1. Now they change to say 1, 0 and no 1, 1 and 0. Now what I am saying that these values are changing together. Now just assume each gate has a delay of delta. So after a time delta, the output of the AND gate will change to 1. Output AND gate was 0 earlier, that will change to 1. Now this value was 1 already, so this output of OR gate is still 1. Sorry, this is not a good example I have taken.
So make it 0 to 1.
Make it 0, 1 0, right? Make it 1 0, yes. Fine. So if it is 1 0, then both will be 1, because this will be 0, okay. But earlier this was 1, so this OR gate was evaluated at this time with the older value, so the output will be 1. So only after time twice delta is this new value will be used to simulate. Now it will take 0 0, the output will become 0. So what I am saying is that,
But here we have assumed that the delays are same as delta delta. What if the delay of the other gate is less than that of the previous one?
delay can be different, because when the simulation is actually carried out, it is an event driven simulation. Depend on the delays of the gates, there will be an event queue which is maintained. The gate which is changing state earliest will be at the head of the queue, that will be a priority queue. That kind of a list is maintained. We will be talking about this later. Simulation is an important part. Yes. Yes. Well, at the logic level, at the pre-layout simulation phase, interconnect delays are assumed to be 0. They are all ideal interconnects. Only at the level of post-layout simulation you can take care of that. Yes, you are right. That we are ignoring. Fine. So now let us again start by looking at very simple examples. Start with a simple AND gate, which was specified in terms of the behavior. So just to correlate with the previous example, module, end module, this is the name of the module, these are the parameters. 2 of these I am specifying as input, 1 I am specifying as output, and assign is a keyword. This assign says that you evaluate the right hand side and assign it to the variable f. So this will typically be synthesized by an AND gate xy, the output will be driving f. Okay, simple.
What else if we don't write assign?
Now assign, you will have to write something, otherwise it will give an error, syntax error. There are different ways of doing it, I will see you. This assign is one way of making the assignment, there are some other ways also, we will see it later. And as I mentioned, that if we have some intermediate wires, for example as this example shows, you can get a 2-level circuit. Here this ampersand means AND, bar means OR, tilde means NOT, and hat means exclusive OR. So actually what we are getting is, we are having an AND gate with A, B as the input, output is T1. This is a NOR gate, okay, OR and NOT. C and D, the output is T2. Then we have an exclusive OR of T1 and T2. This is your F. So depending on the intermediate wires we use, here we are specifying a 2-level logic, right. Well, there are some problems here that can occur during simulation, that we will see later, we will come to it a little later. So that if you are not very careful about it, then our simulation results and the actual synthesis results may differ. Now, even in case of simple gates like this.
Sir,
Yes.
so as you said that these statements are parallel statements.
Yes.
So can we write the third assign line before the second line? Like assign f is equals to t1 caret t2.
That is the problem that can occur. I will come to the example and I will just come back to your answer a little later. That means, what if this you write before t1 and t2? Yes, there is a problem that may arise there. I will just come to that shortly. And this kind of example we had already seen earlier. I am just showing this slide. You can specify a hierarchical design by instantiating modules. Well, like here again you have the ports, you specify some of them as inputs, some of them as outputs. These are the local interconnecting nets, and these are the modules you are putting in. So, here why I have put this is that you can either specify a design in terms of its behavior, or you can specify in terms of its structure. This is a structural design. Basically, I picked up 3 modules, I put them together, I have interconnected them. Okay, fine. Now, as you see from this example, that the way we specify the interconnection is by explicit naming. The cy out 0 and cy out 0 means that the output of this module B0 will go into the input of this module B1. Now, there are 2 ways of specifying such connectivity. One is called positional, which was illustrated in the previous example. Here, the relative positions of the different parameters are maintained. I will assume that the first parameter is the output carry out, second parameter is the sum out, next 2 parameters are the 2 inputs, the last parameter is the carry in. This is the assumption we will use and we will maintain. This is called positional association. The connections are listed in the same order. So, when we instantiate a module, we list the names of the nets in the same order. The first one is carry, second one sum, 2 inputs and then carry in. But you can also choose to jumble up this order. This is called explicit association. There we can list them in any order, but obviously if you do that you will have to explicitly say which one is what. So, you will have to specify it in a way something like this. You instantiate the module and this in1, in2, cin, sum, cout, these are the names which are defined in the parent module description, and a, b, cin, sum and cout are the variables in the present module. So, you say that A is actually in 1, B is actually in 2, cin is actually cin, and this you can specify in any order. So, you can use either of them. Some people say that explicit association is better because your code becomes self documenting. Otherwise, in a just complex layout you may have to go back and forth and see that which one is which. You may lose track of the parameters if there are many. Okay. Now, let us come to the variables. Now, as the examples showed that we had used some variables in our description. Well, apart from the input and output, we had used only one other kind of a variable, that was called wire. Now, let us look at it a little more formally. The variable data types can broadly fall under 2 categories. One is called net, and as the name implies, a net is primarily used to interconnect 2 things, and register. Register, again, as the name implies, it is used to store something, some kind of storage should be associated with the register. Net and register, the main difference is net must be continuously driven. Continuously driven means, suppose I have an AND gate, the output of that AND gate, this can be a net, say F is a net. Continuously driven means if you have an AND gate, you always have some value at the output. There is no time where you do not have a value. Continuously driven means net will assume its value instantaneously as soon as the gate changes state. It will not have to wait till the next clock, right. That's why we say it is continuously driven. It is not synchronized with any other event. As soon as the gate output changes, the net will assume its new value. And this, as I mentioned, this is typically used to model interconnection between modules. Continuous assignment instantiations, we have used those things. So in the examples I have shown, we have used those. And register, as the name implies, it is supposed to retain the last value assigned to it. But you will see later, it is not necessary that always it will have to retain, because the synthesizer at the time of optimizing, it may see that, well, a register variable is, that means a register is really not required. We can use it as a net variable also. Those kind of optimizations can be done. We will see it later. But by definition, a register variable is one which is supposed to retain the last value assigned to it. That means there has to be some storage facility there. So this is used to represent storage elements typically. So first let us look at the net data types in some detail. What are the different kinds of net data types available? See, there are a few other net data types. We are not going into that. We are only concentrating our attention to those which are synthesizable. There are net data types called wired. Wired we have already used in our examples. There is wired OR, wired AND, tri-state, supply 0, supply 1. This wired and tri-state, they are the same. There is no difference between these two descriptions. This wired OR and wired AND, they are slightly different. First let us see wire and tri. Wire and tri, they are equivalent. The idea is like this: if you are using wire or tri-state, say it is something like this. Suppose you use a wire description, let us call it F1 and F2. Okay. Now suppose you have, well, I am just showing the diagram, now I have not shown the Verilog code. You have a gate which is driving F1. You have another gate which is driving F2. This kind of example we have already seen. But you can have another scenario where this gate is driving F1, the other gate is also driving F1. So the synthesizer will not give an error, but what it will do, it will short these two outputs and will give the output as F1. It will not give an error. So the synthesizer will assume that you have taken care, that the designer has taken care that these two gates will be having tri-state control. But if not, then it is a design error, you will be detecting it during simulation. So the output logic value will be showing as indeterminate. But if you are using wired OR or wired AND, suppose I had a description as wired AND F1, and if I had something like this, say an AND gate which is driving F1 and an OR gate which is driving F1. And suppose I had a situation like this, then what the synthesizer will do, synthesizer will explicitly add another AND gate, will connect these two to this and will call the output as F1. Similarly, if it is wired OR, it will add a OR gate. Okay.
But if there is only one F1, then it will AND with 1.
With 1. No, if it is only 1, then the AND will not be there. If it is more than 1, then the AND
It
will
will be same as wire
or also same. So this wired OR and wired AND are similar. They insert an OR and AND gate. And this supply 0 and supply 1 are used because in some cases you may need to supply a constant 0 logic or 1 logic. So you can use these keywords supply 0 and supply 1 to specify that. So let us look at some more examples very quickly. So this is just like the example I had mentioned. There is one one AND gate driving F, there is another OR gate driving F. Since it is a wire type, they will be shorted together, right. So, the way you have specified, this is a wrong specification, it will give a simulation error in the output. And this example again, just the example I have taken, if we use a word AND, this AND gate and this OR gate will have an explicit AND gate added to it. This is very similar, and this example shows that how you can use the supply 0 and supply 1. Well, supply 0 is a data type, supply 0, this is the variable name GND, supply 1 VDD, these are the variable names. And the way I have specified here, I think we have missed something here, there should be another line here, wire T1 T2. Yes. So, this will there will be a NAND gate. There are 3 inputs VDD A and B. This is a 3 input NAND gate, 1 A and B. The output is T1. There will be an XOR gate. This will be a 2 input C and ground. This is C and this is logic 0. Output is T2. These will be ANDed. Output is F. So, here you can specify 0 and 1 constant values also like this. Okay. So, these are regarding the net data types, wire, wire or wire AND, supply 0, supply 1. These are the 5 values you typically use. Now, let us look at the register data type. Register data type, as I mentioned, it is something which is supposed to be synthesized into a storage element. Register data type can be of 2 types, reg and integer. The main difference is that when you define it as reg, you must explicitly specify the size of the storage. Like if you simply specify reg x comma y, this will mean that x and y are single bit variables, single bit storage. Or you can specify in terms of a vector like this, reg 15:0, this will be a 16 bit register. And the convention is that 15 will be the MSB, 0 will be the LSB. And for integer, normally the synthesizer or the simulator will be taking the default size, which is 32 bits. But if you are trying to optimize, then it can do a data flow analysis and it can try to deduce that what should be the minimum possible value of that integer, and it can just use that minimum value. Then I will give an example. I have given, just have an example later, I will show you. And just other than this, this is one main difference. In register, you have to explicitly specify the size. In integer, you do not specify the size. It is the default value is taken normally. And other difference is that you can use the register variables in any arithmetic expression. And if you are using an integer, it is taken as a 2's complement signed integer. But a register value is taken as an unsigned quantity. There is no concept of a negative value there. Okay. This is another difference. And just to give you a broad guideline, you will be using a reg data type for all cases where you are actually trying to synthesize a register or a storage element. But sometimes when you are specifying in the behavior level, you may have to use a for loop kind of a thing. There is the loop index variable, for example, that you can use as an integer. That is just a rule of the thumb. The ones where you know exactly what is happening, you know the size, you specify them as register. The others you can leave it. You can also specify them as register, no problem, but you can also specify them as integer.
So So the input output connections, are they regs or nets?
Input output connections, they are neither reg nor they are just some signals coming in. Their type will be depending on the driver module, the module which is driving those signals. So whether they are driving from a reg type or a
So there also we don't specify, we just write input ABC.
no. Just I am showing that example back. They actually we specify the size. I am showing you the example.
So the size is specified, but the type.
Now type, this by default it is taken to be register. By default this is taken to be register variables. Okay.
So wire is always 1 bit.
Wire you can also use a vector, because in that example of that adder we had used a vector here, wire 1 to 0.
Loop counting statements are synthesizable.
They are synthesizable if the number of loops that is a constant. But if it is some kind of infinite loop or a variable loop, then some of the synthesizers allow it, some synthesizer give error. So now let us look at some examples. Well, there are some features we have not yet mentioned, but you will understand what this means. This is the Verilog description of a simple binary counter with synchronous reset. This counter, if you treat it as a black box, this will be having one clock input, this will be having one reset input, and of course the count value. Clock and reset are inputs, output is the count, and here you can explicitly specify count to be a register. This is another way of doing it. You can basically either specify it here itself, or after declaring you can explicitly say that count whatever is coming, this is a reg.
We cannot do it also. Or we, if we want, we can specify it.
Yeah, if we want we can specify it.
I can do without specification also, I think.
No, yeah.
Then that will take it as 1 bit.
No. Yeah, if you just specify only count, will take it to be just 1 bit. But if you specify the vector, you are specifying the exact
So
size.
then specifying there in the output will be like output reg 31 to 0 count.
Output 31 to 0 count, you can also specify like that. Now in terms of, in the body, this always is a very important statement. You can understand what this means. This will just see later more formally with different options. This says begin end, this is a block. It says that you execute this block every time there is a positive edge on the clock, always at pause edge clock. Similarly, you can specify neg edge. That means there is something like a clock, every time there is a leading edge on the clock, you execute this. This says that if reset is also 1, then count, this is one way of specifying a 32-bit 0 quantity. 32 is the size, apostrophe b means it is in binary 0. So 32 times 0, it is a 32-bit number. This count is initialized to 0, or else count is incremented by 1. So this is just a counter, with every clock it will either increase or it will be reset to 0 if the reset is also high at that time. So this is an example where you have specified reg, and of course in synthesis the counter will be synthesized as a register with storage element.
So here in the first line, so clock and reset, these two are defined as 1 bit.
1 bit.
So in the next line, count will also be defined as 1 bit.
1 bit, you are overriding that definition in the next line. This definition you can override. Just in the input output parameters, you can simply specify this is input, this is output. The sizes you can override in the next statements. That option you have.
So you are telling that output default as register, whatever you would do.
Yeah, output register. You can also specify here output 31:0. That also you can specify. That is one way.
In that case, third line is no less.
third and not this. I have just written this in order to just show you that this is possible to write like this. Okay, now the earlier I had mentioned that instead of register, if you use integer, then the exact size of the variables is not known, but the synthesizer tries to deduce the size of the value. So I have an example to show you that. Yes.
So as you said, if it was not a register, if you written integer in that case,
Here.
so then what will the value of count means in bit format? It will be in 2's complement.
2's complement in arithmetic. Whenever you are doing arithmetic, it will be 2's complement arithmetic. Well, now here it will not matter. It will be the same. Because when
you display the count, if suppose count was initialized as integer,
yes.
then what will it will give in binary format? It will
See.
number or the binary equivalent.
See, if the count was initialized as integer, well, just example, let's take that it is an 8-bit, okay, 30-bit to 2-bit example. Suppose the count value was this, maximum possible positive number in 1. Now after that, whenever you add 1, your count will be this. But if you treat it as a 2's complement number, this will mean minus 128. But if it is a simple counter, you don't care what it means in 2's complement. More important to you is that the count value is this, which to you this is equal to plus 128.
So it is just a
So 1's complement, 2's complement is a way of looking at it.
But so can we specify the input outputs as integers, because you said they have to be regs?
No, you can override the specification here. You can override everything here, but by default they are taken as registers. Okay. Just here a small example to illustrate that when you are using integers, the synthesis system can deduce the exact size of the value. For example, if you have a description like this is a Verilog code segment where 1:10, you can also specify like this. This means 10 will be your LSB, 1 will be your MSB. Numbering you can specify in whatever way you want. Integer C, and in the computation part you write C equal to A plus B. Now by using a data flow analysis, the synthesizer can deduce that A is a 10-bit quantity, B is a 10-bit quantity, and we are adding them up. So the sum can be 10 plus 1, 11. So there will be 10 bits for the sum and 1 carry. So C will be synthesized as a 11-bit register in fact. So often the synthesizer tries to do this kind of data flow analysis and try to deduce the value of C instead of by default taking it to a 32-bit register always. It can try to find out what can be the maximum value possible. It can take it to be that.
Let's say here you haven't written assign.
No, assign I have not written. Just as an example, I have just written 3 statements.
But
This assign will also be there. Assign will be there. Assign will be there. Just this is the last slide I am showing. This example I have already shown this example in one of the examples before for the counter when you initialize to 0. So how do you specify constant value? Well, a constant value you can specify like this also by simply specifying the value 25 for example, or you can specify the size in terms of the number of bits, then an apostrophe. Base can be binary, hexadecimal, and the actual number. There are different ways of doing that. See, 8 base B, this means this is a 8-bit binary number and this is the value. So when I specify binary, I have to give this value in binary. 12-bit hex, this is the hex value. 12-bit hex, this is the hex value. 1-bit binary, this is the binary value. 1-bit binary value. Now, in the earlier example, we had written something like this 32 bit binary 0. This means this is a 32 bit binary number with a value 0. So, the value 0 means 32 zeros. So, all 32 zeros will be assigned.
So how to specify value in unsized form means?
Unsigned form, it is up to your interpretation, means whether it is signed or unsigned, it is up to your interpretation, because these are constant values you are assigning.
No, unsized form.
Unsized, well, unsized, if you do not specify anything, simply 25, default is 32 bits, like this, just to simply specify.
And will be taken in decimal.
It will be taken in decimal, yes, it will be taken in decimal by default.
You can assign it to a wire or something.
You can assign it to a wire. You cannot assign it to a wire, you can assign it to a register. Because a constant cannot drive a wire, only another module can drive a wire. So in the next class we will be continuing from this point onwards. We will be looking at some other features of the Verilog language, how to specify constants in terms of something called parameters, and this always block will be looking in some more detail. And in fact, here for the timing we have looked at only at ways of specifying combination logic, and only one counter we have seen, but we will see that depending on the design style, it will depend exactly what hardware will be synthesized. Okay. So, if we have something on the back of our mind, for example, we want to synthesize a decoder, we can write our code in that way, so that a decoder will be synthesized, so that we can force the synthesizer into synthesizing it in a particular way. That is possible. That we will see slowly during the next few classes.
So you said that the wire has to be continuously driven.
Wire has to be continuously driven.
So suppose like the output of AND gate, it
Yes.
is a high impedance state. So what is the wire?
Output of an AND gate is a high impedance state. It is continuously driving the wire. That means the wire is having a value X or Z. Z is high impedance. So Z is also a valid value, 0, 1, undefined, don't care. So actually when you are saying it is continuously driven, it means that it will have a value at all times, but when it is clocked, only when clock comes the value will change. But if the output of the AND gate changes from 1 to a high impedance state, the wire will also change to a high impedance state. Okay. It is not clocked. So let us stop for today. We will be continuing with our next lecture.